and welcome everybody, and thank you for joining our webinar today. Our topic is ARM's latest processor core for MCU applications, the ARM Cortex-M7. I will first give you a general overview of the ARM Cortex-M architecture and its advantages for embedded developers. After that, we will dive into the details about the Cortex-M7 and the new features it brings compared to previous cores. And lastly, I will show you the Cortex-M7 based MCUs that are already available from our partners. ARM offers 3 different profiles of processor cores, which can be used in a wide range of embedded applications with different requirements. ARM does not manufacture silicon itself, but licenses its processor cores and other technology to the semiconductor companies which design it into their products. The ARM Cortex-A processors, like the Cortex-A or Cortex-A57, are most well known from their usage in mobile applications, but they are also very common in embedded applications, like advanced driver assistance systems that require high performance and the use of rich operating systems like Linux or Android. The Cortex-R cores are probably the least well-known, but are actually used in many very high-volume applications like hard disk controllers or engine control or mobile base stations. They combine low-latency real-time behavior with high performance. Our main focus today are the ARM Cortex-M processors, which are mainly targeted at embedded applications, from industrial control to white goods, toys, wearables, and what we now call Internet of Things devices. The Cortex-M profile currently contains 5 processor cores. In order from lowest to highest performance, these are the Cortex-M0, M0+, M3, M4, and M7. MCUs based on Cortex-M0 and M0+ are an excellent replacement for 8 and 16-bit MCUs, with low cost due to the small silicon area requirements and a very high energy efficiency. The Cortex-M3 was the first Cortex-M core with MCUs released in 2006 and is now widely used by a large number of silicon vendors. The Cortex-M4 adds floating point and SIMD capabilities to the Cortex-M3. And finally, the Cortex-M7 is the latest addition to the family, launched in September 2014, and with MCUs now becoming available in mass production. Choosing the right core for your application is an important step in your project. Just because the Cortex-M7 delivers the highest performance and higher performance than the Cortex-M4 does not mean that it is better for all requirements, as you also have to consider power constraints and cost. At this time, I'd like to ask you to answer our poll question about your previous usage of MCUs with ARM processors. So if you now look at the polls pane, you can see the question, which cores have you used before, and I'd like for you to reply now, and we can look at the results later on. Now let's look at the instruction set that is supported by all Cortex-M processors. First, a bit of history. One of the more successful processor products from ARM is the ARM7 TDMI, which is a 32-bit core processor and includes Sorry, I had some technical difficulties here, which includes the thumb architecture, which is a mixture of 32-bit operations and 16-bit instructions. And this allows a very, very high code density, and it has been developed into the Thumb2 instruction set, which is a performance-optimized blend of those 16 and 32-bit instructions, which again enables very high code density, and that is supported across all ARM Cortex-M processors. If we take a look at the baseline programmer's model that is shared between all Cortex-M cores, we see that there are 16 registers, with the last 3 having special usage. Register 13 is the stack pointer. Register 14 is the link register, which stores the return address when making a function call. And register 15 is the program counter. There are a few other special registers. The XPSR register, the program status register, provides ALU flags and various processor status information. Note that the stack pointer is banked. The second stack pointer is used when an operating system is used in your application. 1 bit of the control register is used to control which stack pointer is used. There's also a 1-bit register called prime mask for interrupt masking. There are some differences between the Cortex-M0, M3, and M4 in the control and XPSR registers. For example, the M3 XPSR is a superset of the one in the M0, and in turn the M4 XPSR is a superset of the one in the M3. Cortex-M3, M4, and M7 have additional special registers. There are 2 modes in the ARM Cortex-M architecture: the thread mode for normal programs and handler mode for exception handlers, for example, interrupt service routines. In parallel to these 2 modes, there are 2 privilege levels, privileged and unprivileged. Handler mode is always privileged, and thread mode can be both either privileged or unprivileged. The parts of the software running in unprivileged mode cannot access some resources like the system timer or the system control block. So any parts of the software that should not access those system level control functions can be run in unprivileged mode. Now let's take a look at the memory map. The 4 GB linear memory space is common in all Cortex-M processors, and all locations are accessible by software. The memory space is partitioned into a number of memory regions that are assigned to typical usage types. These include program access code, which is in the code region, data accesses, which is in the SRAM region, peripherals in the peripherals region, and the processor internal control and debug components in the system region. There's also an optional memory protection unit which is available for the Cortex-M0+, M3, M4, and M7, and can be used to define memory access permissions. A very compelling user case for the MPU is to define privileged and unprivileged regions in memory for high reliability systems. Cortex-M processors have multiple sleep modes, and the processor has multiple clock signals to control those sleep modes. In sleep mode, the main system clock is disabled, but has some parts of the logic, for example, the SysTick and the interrupt control logic, still running for interrupt detection. In deep sleep mode, it is possible to disable all the clock signals to the processor using the wake-up interrupt controller, the WIC, for interrupt detection. The WIC is a small extra block that sits outside of the processor so that you can let the processor sleep, and the wake-up interrupt controller is waiting for signals to wake up the main core. If special state retention power gating technology is available in the semiconductor manufacturing process, the processor can be put into a state retention power down state. The only power need then is for state retention, the wake-up interrupt controller, and the power management unit. The wake-up interrupt controller is used for interrupt detection during such a deep sleep mode, and when an interrupt comes in, the wake-up interrupt controller informs the power management unit to restore power to the processor, and then the processor restores its states and resumes operation. Most MCU vendors implement their own sleep modes on top of those that are defined in the architecture with various power levels and wake-up procedures in their products. The Cortex-M processors have an upward compatible instruction set. In this picture, we see small bubbles for the 16-bit wide instructions and larger bubbles for the 32-bit wide instructions. The data is always 32-bit wide. The instruction set of the Cortex-M0 and M0 Plus processors consists largely of 16-bit instructions, and they adhere to the ARM v6M architecture. The Cortex-M3 adds data processing and bit field manipulation instructions as defined in the ARM v7M architecture. The Cortex-M4 and M7 add instructions for digital signal processing and for single instruction multiple data access. And the Cortex-M4 and also the M7 have an optional floating point unit with single precision accuracy, and after all, the M7 has an optional floating point unit with single or double precision accuracy, and therefore has the matching instructions. Now, if I say a processor core has an optional FPU unit, that means that ARM offers this as a licensing option to its partners, but the MCU vendors have to decide whether they want to put an optional unit into their MCUs or not. So some parts are mandatory. If you license a Cortex-M core, those have to go in there. Other parts are optional. A floating point unit is one of these things. It is available on the vast majority of Cortex-M4 cores, but not on all of them. On to the interrupt management system. The interrupt handling is built into all Cortex-M cores and is a unit called the Nested Vector Interrupt Controller, or NVIC for short. The NVIC supports a number of interrupt sources, a non-maskable interrupt, a SysTick timer, and a number of system exceptions. The NVIC has a number of programmable registers inside, which you can use to set up priority levels for interrupts, or enable and disable them, and so on. The NVIC handles nested interrupts automatically. So for example, if a high priority interrupt comes in, it can preempt a running lower priority interrupt, and the processor will automatically save some of the context using stacking operations. Now we'll take a look at debug and trace logic, which runs under the name ARM CoreSight. And on this slide, we can see an overview of the different CoreSight modules that are present on a Cortex-M microcontroller. The run control module provides basic start, stop, and single-step debug functions. The breakpoint unit provides up to 8 hardware breakpoints. The memory access unit gives the capability to perform on-the-fly read and write access to memory and peripheral registers. So this works with the running processor. You don't have to stop program execution to read or write memory values. The embedded trace macro cell, or ETM, can be used for instruction tracing to debug historical sequences or for software profiling and code coverage analysis. ETM data is usually output through an extra 4-bit interface. The instrumentation macro cell, or ITM, provides instrumented data trace such as printf output. So you can put printf statements into your embedded program, and the output goes directly through the debug channel to your development environment. Data watch point and trace unit, the DWT, provides program counter sampling, event counters, timing, and interrupt execution information. In addition to that, it allows access breakpoints for up to 4 memory addresses. So if those addresses are accessed from any program location, then it can automatically generate a breakpoint event. Again, it depends on the MCU vendor which debug and trace mechanisms they actually implement in their MCUs. So usually, for example, you can have the ETM, the instruction trace macro cell, in all Cortex-M3, M4, and M7 MCUs, but it is not actually added to all of them. Some vendors leave it out. To use the debug functionality, there exists a huge software ecosystem around Cortex-M processors so that everybody can find just the right development and debug tool for their requirements. Now, after this general introduction to the ARM Cortex-M MCU architecture, we'll take a look at the newest core, the Cortex-M7, and its new key features. The M7 is the high-end member of the Cortex-M family, and it's targeted at various markets as a replacement for often used combination of an MCU with a proprietary DSP. It's applicable as a sensor hub, for example, connecting many sensors via I2C or SPI and managing the data that comes in. It's applicable to as a factory automation controller or in automotive applications. For smart devices of all kinds, the Cortex-M7 based MCUs offer up to twice the performance of Cortex-M4 based devices, which makes it suitable for much more demanding requirements like voice control or advanced touch sensing in devices both in the gadget market or wearable market, but also for future white good applications. The higher performance of the M7 can also be used for control applications to be able to provide improved signal processing. So we have on this slide an example of an autonomous drone that can use the improved performance of a Cortex-M7 device for much more accurate speed measurement, better GPS accuracy, and resulting in that in much better overall performance. The performance is also very applicable to audio application, where these can greatly profit from increased performance to enable higher channel counts or higher quality audio codecs when compared to solutions using the Cortex-M4. Now, if we take a deeper look at what's been added to the Cortex-M7 to enable these large performance improvements, we see that firstly it has a six-stage dual issue in-order pipeline for efficient operation at higher clock rates. The Cortex-M7 is already available at higher clock rates than MCUs with Cortex-M4, and we expect for the coming year or so even faster MCUs to appear on the market. Secondly, the M7 offers an option for the double precision floating point unit. And as I mentioned, the option in this context means that it's available for licensing, but the silicon vendor itself has to decide whether to include it in their product or not. Current products they do not offer double precision floating point, but I'm sure we will see these products coming out in the coming months. The third point is the Cortex-M7 design includes caches for data and instructions, and also tightly coupled memory that sits closer to the core to avoid bus accesses and wait states for frequently executed code. Together, these features enable the ARM Cortex-M7 core to reach up to 5 core mark per megahertz, which is a lot more than comparable MCU solutions. Lastly, there's an option to include memory error correction codes for safety relevant applications, and ARM provides a safety documentation for the MCU vendors licensing the processor core to enable them to qualify their parts for functional safety applications. If we take a look at various digital signal processing algorithms, we can see that the M7 core is on average twice as fast as an M4 if we take the expected clock speed increases for the M7 into account. The functions listed here are all part of the ARM SAMV DSP library, which is provided free of charge to all customers and includes code optimizations for all Cortex-M cores. It is portable, meaning that if you have an application on Cortex-M3, for example, that uses DSP algorithms, those are done in software. If you then decide to move on your design to a Cortex-M4 core, you can run the same code, just need to recompile, and the SAMV DSP library will automatically use the hardware acceleration that's on an M4 core or on an M7 core. Looking at the memory system, a first in the world of the Cortex-M MCUs is the support for data and instruction caches, which can speed up memory access tremendously. Tightly coupled memory for both data and instructions has the same goal but works differently. Whereas the cache is filled with data and instructions by the cache logic during the regular program flow, the developer statically places important data and instructions in the tightly coupled memory. And this can, for example, be done for interrupt service routines that are executed often and require low latency response. You would put these into the instruction TCM, the tightly coupled memory, and therefore when the CPU has to execute code from that interrupt service routine, it can get those instructions into the CPU core a lot faster than if it were to read them from flash memory. For functional safety applications, the Cortex-M7 offers some key features like deterministic execution with high performance and an in-order pipeline, as well as optional memory error correction code, as I mentioned previously. The full instruction trace using the ETM, the execution trace macro cell, helps with both debugging, and it also greatly simplifies the process of gathering the required data for certification purposes, as you can easily prove code coverage with ETM and the tools. I now want to show you the ARM Cortex-M7 MCUs that are currently available on the market. The first one is the STM32 F7 family, which is pin compatible with the STM32 F4 family, which is Cortex-M4 based, and is available with clock rates up to 216 megahertz and up to 2 megabyte flash memory and up to 320 kilobytes of RAM. It includes 4 kilobytes each of dedicated data and instruction caches, as well as 64 kilobyte of tightly coupled memory for data and 16 kilobyte for instructions. ST offers the low-cost discovery boards with the STM32 F7 parts. Those are displayed on the top right, and also the high-end eval boards, which have a large amount of connectivity options. So essentially all peripherals that are available on the F7 products are available on this board. The other family I would like to show to you is from Atmel. Atmel offers Cortex-M-based MCUs in their SAM-E, the SAM-S, and SAM-V families. And these devices run with up to 300 megahertz, which makes them achieve up to 2,000 core mark in total, which is unprecedented in Cortex-M devices so far. They each have 16 kilobyte of data and instruction cache, and that sits next up to 2 megabytes of flash memory and up to 384 kilobyte of RAM. And this SRAM can be user configured to include data and instruction tightly coupled memory. So it's a flexible solution where the developer can decide whether they need a large amount of RAM, then they can configure that, or if the developer thinks they need a larger tightly coupled memory for data or instruction, they can also configure that. So the SRAM can freely be configured between TCM and RAM usage. There is one board currently available from Atmel, that's the SAMV71 explained Ultra board, which also offers most of the connectivity that is available on the SAMV Cortex-M7 based devices. In addition to Atmel and ST, Freescale has also announced their Cortex-M7 based Kinetis KV56 and KV58 parts. And these are still in pre-production phase and will become available later this year. If you want to learn more about how to develop with these Cortex-M7 based devices, we would like to invite you to part 2 and 3 of this webinar series, in which we will show you how to get started with the devices from ST and Atmel and the Kyle microcontroller development kit. The ST webinar will take place on Tuesday, 1st September, 3 p.m. UTC, so same time as this webinar. And the second one will take place on 15 September, also 3 p.m. UTC. That's all the content we have for today. Thank you for attending.